Okay, so I hope you can all hear me clearly and also read the board. I will try to write a little bigger today, but let me know if things are working all right. So just to quickly summarize where we were, at the last lecture. So we actually spent 2 or 3 weeks, I think, talking about the basic model, this basic two-band model, depending on conditions, called the Kondo lattice or the Anderson lattice model. And the basic structure is you have one band C, which has weak interactions, and another band D, which has strong interactions. And this is a very common situation in certain intermetallic compounds, where there are two different ions which are contributing conduction electrons that move around. One of which is a D or F band metal, and the other is a lighter metal. So the lighter metals tend to have weak interactions, and the D and the F bands tend to have strong interactions. And the upshot of all the analysis we have done is that these kind of models tend to can have two different types of metals. These are metals which are neither of which breaks any symmetry, but nevertheless are distinct quantum phases. One of which is the heavy Fermi liquid. And this is the phase you would get if you started from the zero interaction limit and expanded about that. Then you obey the usual Luttinger relation and you get a large Fermi surface that counts all the electrons. And the other phase is the FL star phase, of which there are occasional sightings. This one is seen in many cases, where basically to zeroth order you can think of it as the sum of two phases. There's the spin liquid phase of the D alpha, the strong interacting band, and then the small Fermi surface phase of the conduction electrons. And the content of much of the analysis we did is to show that this kind of decoupled picture of a spin liquid coupled to a Fermi surface is stable to interactions and gives you a new phase, even when they're not decoupled. Okay. So this situation is actually somewhat analogous to things that also happen in quantum field theory, where people talk about coupling a topological field theory, which is what this spin liquid is, to some kind of conformal or gapless field theory, which is what the Fermi surface is. And in this case, and also in many of those cases, the basic decoupled structure is stable. In this case, the size of the Fermi surface is stable to all orders in the coupling between these two. Okay. All right. So, but this naturally raises the question, is this the only way to get an exotic metal by just adding a spin liquid to a Fermi liquid? So we've just added, the first part of the course to the second part of the course, and that's really all we've done. Anyway, okay, so that's the summary. Any questions from last time? I've actually updated the notes a bit, so please download the notes, especially on this issue of the Oshikawa argument and this spin liquid response to flux insertion. I've clarified that in the notes quite a bit, I think. Anyway. All right, so any questions? Yeah, you had a question earlier, right? Maybe.
So in the last class, you write this Chern-Simons theory for G2 spin liquid.
Yeah.
Can you give some brief idea how did you write that theory?
Yeah, so I guess you had earlier mentioned, is it sort of like the Chern-Simons term where you, for a chiral spin liquid, where you integrate out the spin-ons, and then you get a Chern-Simons term where that comes from the band structure of the spin-ons having a Berry curvature and a Chern number. In this case, it's rather different. This particular type of Chern-Simons term is a mutual Chern-Simons term. It doesn't break time reversal symmetry, and is not associated with any topological band of anything. There's various ways of deriving it. They involve applying particle vortex duality to some of those methods we developed to analyze the Z2 spin liquid. That's actually We've not covered that in this course. It will be in the book that I'm writing. But roughly speaking, you can kind of derive it by hand. So, you have the E and the M particles. They're both bosons, and they pick up a phase factor of pi when they go around each other. So we just try to write down some Chern-Simons theory which has that property. And when you do that, you'll pretty much get the theory that I wrote down. Okay. But actually, in the updated version of the notes, I've derived this flux insertion phase factor that you pick up for a Z2 spin liquid directly from the wave function with Z2 spin liquid without using the Chern-Simons theory. So I won't go through it on the board, but it's in the notes. It's an old argument. I mean, the argument is actually very similar. This new the way I presented it now in the notes to the old Lipschultz-Mattis argument for one-dimensional spin chain. You do almost exactly the same thing, but in 2 dimensions. And they showed that when you apply a slow twist to the spins, you pick up an extra phase factor, depending on the system size, the order even, and exactly the same thing happens here. Yeah. No, sorry, there was no odd and even in their case, but it's basically the Lipschultz-Mattis argument applied to a bunch of chains parallel to each other. Okay, and that works, and it gives you the same answer. All right, any other questions? Anybody online? Okay, so now that we have developed all this technology, we've learned about Fermi liquids, we've learned about strongly interacting metals, we've learned about spin liquids. The temptation is irresistible to finally talk about the elephant in the room, which is the cuprates. I haven't said anything. I mean, we talked about the cuprates early on, where I just did various mean field theories, Fermi liquid type theories to them. And I mentioned it doesn't work at all. So now we have this this beautiful structure of 2 possible metallic phases. Can we apply this to the cuprates? So as we'll see that if you just look at the cuprates without knowing anything about what's in them, just look at the experimental observations, they look remarkably similar to this kind of distinction, which I'll review briefly. There's one regime where it looks like a Fermi liquid, another regime where it looks like FL star. But the big problem, of course, is the cuprates are not 2-band models. There is no natural way to say these electrons will form a spin liquid, these electrons will form a conduction band. In a 2-band model, it's a very nice way, a simple way to say that. And that, in some ways, is at the heart of the difficulty of the cuprates, I think, and why for so many years we still, there's a lot of progress, but there's still many open questions. So let's talk about that now. And I want to present some relatively recent ideas building on work by many people over the years, which I think are, at least in my opinion, getting quite close to applying these ideas in a systematic way to the cuprates. Okay, so we'll talk about a 1-band model. And ask, can you get anything like this? So, we're going to start with the Hubbard model, of course, minus T, E dagger I alpha, Cj alpha, plus U and I up, and I down, and some chemical potential, which I won't write out. Okay. And we are interested in the limit, of course. The interesting regime is U much bigger than T. We said a lot about this in perturbation theory in U and various other 1/U expansions. But we ended up, in the end, with phases that were rather conventional. Okay, so if I draw a picture here of what we want to talk about, so you have a bunch of electrons on the square lattice, which whose spins can fluctuate. And there's also holes around there, something like this. And your U is so large that you don't want to put two electrons on the same side. Okay. Anyway, something like this. So the density of holes defined this way, defined with respect to a system where you have one electron per site, and this is how people measure it, is equal to P. So this P is a very important number to keep track of. Okay, yes?
Hey, Subir, what is the most compelling experimental evidence that this one-band model captures the low-energy universal physics of cuprates?
Well, the question is, why don't we use a two-band model?
Or some of these three-band models, including oxygen,
right.
etc.
So I would say that there is absolutely no question that it's a one-band model, and the evidence is photo emission. If you look at the Fermi surface, let's say, optimal doping or above, you only see one band, okay? You never see a second band anywhere close to the Fermi level. Now, there's a separate question. Is that quasi-particle that's near the Fermi level, is that on the copper or the oxygen or somewhere? Who knows? It's some complicated combination. So if I want to really describe that physics of where microscopically is that quasi-particle on the Fermi surface sitting, then I really need to go to the microscopics and put in 2 or 3 band models and solve them. But if I'm not interested in that, if I'm just interested in the physics near the Fermi level, down, so quite about, I don't know what the scale is, 50 milli-electron volts or something like that, which is the whole range of photo emission experiments, maybe 100 milli-electron volts. You never see another band anywhere. So I think this whole question is really moot. I mean, maybe for some issues, you need to put 3 band in, depending on you want to really get some microscopic details right. But if you're just talking about some effective band, which is near the Fermi level, which you're going to use to describe phases like this, there's only one band. There's absolutely no question about that. Yeah. I mean, so of course, I'm also not saying it's literally the Hubbard model. You could start from some higher band model, and eventually you may get further neighbor hopping, you may get second neighbor interactions and so on and so forth. But then you never get another band near the Fermi level. And it's never ever been seen in any experiment. So yeah, so that whole debate should be completely put to rest. Sorry. Okay, so what was I saying? Right, so now the question we can ask, now thinking very naively, there's a very naive way to see that actually there are 2 different types of metals possible. One way, and the way is the following. So one thinking is, so now I ask you, what's the density of charge carriers in this system? So if I'm just a purely classical person, I see these electrons sitting around, 1 per site with a few holes. And the holes are the ones when they move that carry the charge. So from a very naive thinking, so the classical reasoning, let's put it that way, you would say the density is P. Of carriers is P holes. Let me not put in brackets because these are not holes in the proper sense, because there are holes in this thing where I'm just ignoring the spin of the electrons, if you wish. All right. On the other hand, if I do the kind of counting I did here, when we counted electrons here, we always counted them in the 0 interaction limit first. That's how you start. Maybe not in FL star, but certainly in here, this is what you had to do. But here, you had a natural reason for not counting these electrons because they were in a different band. Here, there's no natural reason to not count all of them. So you would say, well, what are these holes in? Well, in band theory, holes are always in a filled band. So band theory reasoning would tell you that, well, if you had a fully filled band, there's 2 electrons per site. And now I have 1 minus p electrons. So the number of holes with respect to 2 is 1 plus p. I'll tell you density is 1 plus p. Okay, now again, this is looking very similar to here. We had here a large Fermi surface with density of electrons 1 plus rho c, and here you had just rho c. The shift of 1, depending upon how you count these holes. So that looks very suggestive. And in fact, if you now can just look at the experiments. And so let me just tell you a little bit about the experiments. Okay. So in experiments, there's the low doping regime, sometimes called the pseudogap regime, where it seems like in many experiments, it roughly looks like there's p holes. And there's a high doping regime where there's 1 plus p holes. So that's pretty much what you see. So this very naive theory really works. So this is the famous phase diagram of the cuprates. At p equals 0, you have the antiferromagnetism, which just disappears fairly quickly. So I won't say much about that. Then, of course, here's the famous ITC dome. This is the superconductor. And I won't say anything about that today either. But let's imagine, we'll take some temperatures, say about 100 Kelvin. And there's a lot of very complicated things that happen below 100 Kelvin, including the most interesting thing. But there's also a number of very interesting that happen above 100 Kelvin, and that's what I want to understand. Now, one point of view of many people is that that's totally misguided. We should first understand what's happening down here, and then fluctuate or whatever is happening here, and that will tell you what's happening up there. I don't buy that point of view. I think 100K is still very low compared to the exchange coupling J, which is 1800 Kelvin or something like that. So it's still a very low temperatures, and we should really think about what's happening here as quantum phases in their own right. We should be able to describe them and fit the experiments. And just thinking of these as quantum phases, which in some theoretical world or in some quantum simulator that somebody will build someday, will also go all the way down to 0 temperature. And of course, the test of this idea is, can you then fit the data? Okay, and we had a paper yesterday on the archive where we're fitting a lot of data. So anyway, so let's see where that goes. But put that aside, what are the facts? The facts is you see 3 different metals separated by crossovers. Over here, and in fact, even down below, you have the Fermi liquid. So if you do photo emission experiment, there's lots of beautiful data like this. You see a Fermi surface, which looks something like this. Okay, and these are the occupied states. This is Kx, this is Ky, from minus pi to pi. Okay, so there's some band that crosses 0 energy, and you can even see the band below and a little bit above in photo emission. And you always, everywhere, see only 1 band. No one's ever in an experiment like this seen 2 bands. Okay, and then you can measure the area of this region. This picture is not to scale. So these regions, if you measure the area, this one, the area is 1 plus p, with factors of 2 pi squared and so on to get the phase space right. So basically in this region, everything's fine. You can do small U perturbation theory. You can do density functional theory, and people have certainly done it. And you can even get the shape of the Fermi surface and even some estimates of the quasi-particle mass, and it all works, remarkably well. Okay. All right. So then, of course, the big puzzles are these other phases. And the point of view, as I mentioned, I'm taking is that once we understand these phases, then we can ask about various instabilities of these phases at low temperatures. And then we can address the issues here. All right, okay. So this phase is often called the strange metal. More recently, people are calling it the Planckian metal. I'll eventually say something about this next week, probably. So that's where there are no quasi-particles. But today I want to talk about this metal down here. I guess it's often called the pseudogap. And it's also a metal. Metal in the sense that if you lower the temperature, the resistance goes down. So it has finite resistivity. And in fact, even if you come all the way down here, there it goes superconducting, the resistance goes to 0. All right, so what do you see in the pseudogap metal? So this is still, work in progress, but there's a lot of experiments now. Photo emission is a bit mysterious, although there's a lot we know from photo emission too. And there have also been various angle-dependent magnetoresistance measurements and quantum oscillation measurements in high fields, and so on. I have my own understanding of all those experiments, which I think hangs together, but it wouldn't be fair of me to say that everybody buys it. I mean, there's a lot of other opinions. So all we can do is tell you my opinion. So anyway, so what everyone agrees with is the Fermi liquid model doesn't work in this regime. You have to have something more. Okay. So among, if you looked at the photo emission experiment, you see these famous Fermi arcs. You see some arcs here, something like this. And then, but you don't see anything out here. And here, if you looked at in this region where you see these zero energy lines, they're completely gone. So that's why it's called a pseudo gap, because there's a gap at the Fermi level. It's as if those electrons are not there. They always have a high energy. They have a very interesting dispersion. And the model I'm going to present, in fact, models that dispersion very well. Okay, so that's photo emission. Then there's these various magnetoresistance measurements. And that's the primary one. And I guess there's also some Raman scattering and so on. But the natural conclusion is that, in nobody's theory do you ever get Fermi arcs. A Fermi surface can't just end in nothing. It has to be a closed curve. So the natural conclusion is that actually these things close back, but just the intensity of that is very weak at these temperatures. Anyway, so there's various ways of estimating what the size of that pocket is, as they're called. And if you measure the area of these pockets by various measurements, and that would take a long time to discuss this, the area here, in fact, is T. Again, consistent with this very naive argument, but that naive argument certainly doesn't have enough meat in it to produce a calculation of the electron spectrum. Okay. So, very naively, if the cuprates really were a two-band system of like a condo lattice, then the whole story would be over. We very easily understand this, but they're not. And that's really at the heart of the problem. Okay. So there have been a lot of ideas on how to understand this, and over the years, including many papers by many distinguished people. So what I'll do is just present in the next 15, 20 minutes some recent ideas which put together much of the older work. I won't have time to give proper credit on the board, so I'll just tell you the recent ideas. What I like about our recent ideas is that they give you a very systematic and controlled way of computing things, and also give you a very simple picture of how you could get an FL star phase in a one-band model. All right.
One question, may I ask?
Yes, please.
What is known about the temperature dependence of the Fermi arcs? Probably there is some confusion.
Well, I mean, there's some evolution that people study, but that's in the superconducting phase. When you're in the normal state up here, I don't think there's much of a temperature evolution. You never get low energy excitation out here.
Okay.
You can get sharp quasi-particle in the superconducting phase here, but the quasi-particles are very broad and also are rather high energy.
And the length of the Fermi arcs remain almost the same?
Yeah, I believe. I mean, yeah. I think the better way to actually measure whatever is to look at magnetoresistance measurement or some transport probe. So a transport probe, unlike photoemission, doesn't take an electron out of the sample. And when you take an electron out of the sample, there's a wave function overlap factor, which we call Z, which is very small at the back of these pockets in anyone's calculation. So photoemission is not the best way to detect the pockets, but if you do magnetoresistance measurement, the factor Z doesn't appear at all. And in principle, you're seeing the backside equally as you're seeing the front side. So there's a recent paper by Brad Ramshaw and Louis Taillefer, who done some modeling of the angle-dependent magnetoresistance, and some model of pockets like this is really the only one that fits their data. And those pockets are just only dope independent, or at least over the temperatures I mentioned, the area enclosed by them.
Thank you.
Subir, the area being P and 1 plus P, is that some sort of generalized Latinger theorem for the holes?
Well, we wish if you had a theory for this phase, yes. So I have to give you a theory why that's 1 plus P, why this is P. 1 plus P is not a problem. But here you have to form a spin liquid somehow to get a new type of Latinger theorem. Well, maybe I'll tell you the hand waving picture, which goes back actually originally probably mentioned first by Wen and Lee, of how you get FL star. So the hand waving picture is the following, but it doesn't. The difficulty with it is that again, like this hand waving picture, it's better than this hand waving picture, but it's very hard to compute anything with it.
But we were just trying to understand how the pseudogap phase, as you increase doping, then becomes.
Sorry, I can't hear you very well. Maybe if you can remove your mask for a minute.
Can you hear us now?
Yes.
So we were trying to figure out how, if you keep doping, the pseudogap phase will end up becoming the Fermi liquid phase.
Okay. Yeah. So that's let's just leave that. That's one of the big open questions. Yeah.
And it has to go through this strange.
I mean, first we need a theory. I mean, I think the logical order I would say is first you need a theory of the pseudogap, then you can look at its quantum phase transitions to the Fermi liquid. And there's no shortage of papers on that, including by me, but I won't talk about it right now.
And one more question, actually, we didn't quite follow. Why does the photo emission spectrum give you both? I mean, only one line or not the second line, something that you said? was little
Well, there's this quasi-particle residue. When the Green's, if you write on the Green's function, it has a z factor in the numerator, which can be momentum dependent. And so the assumption is that the z factor is rather small on the backside of the pockets.
I see.
And that's typical in any kind of modeling that people do, and including the model that I'm going to present. And it's also these measurements are at finite temperature, so things get washed out. Now, if you could really, photo emission has come a long way. It's a very precise tool now. If you could really do these experiments all the way down to low temperature, then probably you'll see the whole thing. But other things start to happen when you lower the temperature. Yeah. So in fact, what we are focused on really is not so much the arcs, but the gap regions, where there's also a lot of non-trivial information that I haven't discussed. But if you look at paper yesterday on the archive by various people, including me, we discussed a lot of that and see how this kind of FL star model can fit that. Anyway, I was going to present a very naive picture of the pseudogap. So the naive picture is the following. First of all, you say that these spins form singlets. Okay. So the spins form singlet. Let's start from scratch. I mean, I just shouldn't say naive. It's some kind of extreme spin liquid picture where all the singlets are short ranged, which is of course far from the real situation, but no worries. These will give you the idea. Okay, so the sum of the spins form singlets. I'll put them in orange. So each orange is 1 over root 2 up, down, minus down, up. Okay, 2 electrons in a spin singlet bond. And the whole RVB picture is these are resonating. Okay, and they're moving around, and there's a few holes left over too. Okay, so on. So these move around, and there's some empty sites. And the empty sites are really empty, so there's just 0. Okay, so now I have these holes. People better call them hole-ons because they're holes in a spin liquid. And the density of these holes is P. So this particular, now these hole-ons form the metal. You get a small Fermi surface of these hole-ons, the background of a spin liquid. And you say, oh, wonderful, it's all done. I have a doped spin liquid with these hole-ons moving around, density P, and I can explain the experiments. There's only one problem with this. These hole-ons are not electrons. So when you eject an electron in photo emission experiment, you have to eject both the charge and the spin of the electron. These don't carry any spin. So what you have to do is you have to break a bond and get the spin of that electron there and eject it. And so when you do that, that costs energy. And in fact, you won't get any spectral weight at the Fermi surface. So even the front side of the arcs you wouldn't see. So this, and there's various other experiments that show clearly this kind of picture doesn't work. Really, the point here is that the small Fermi surface here is not an exotic Fermi surface. It's just a very simple Fermi surface of electrons. So how can you fix that? So the picture is the following. So imagine that some of these spins, so it's, you can see it's quite there's a bunch of steps that you have to take, and you're not quite clear what's going to happen. So some of these spins now get free, okay? And now these spins will be attracted to the empty sites because then they can hop around more rapidly. So perhaps they form a bound state, okay? So what I'm going to do then is I'm going to have a state, which I'm going to describe this way. I have some orange dimers, and I also have some yellow dimers. So what are those? Okay. Okay, so then I'll put some yellow dimers. I hope you can see the difference. Yeah, orange and yellow. And maybe over here. And what is a yellow dimer? A yellow dimer is equal to 1 over root 2 of the whole, let's say plus the whole and here. So this is like a very tightly bound state of a hole and a spin. But they're on the, okay. And now this is, you're almost there. What is this yellow object? Well, it has a spin a half, it's charge E, so it has the same quantum numbers of electron. And it's a fermion. It can move around from a Fermi surface. And the density of the yellow objects is P, because each yellow object has exactly one hole. And there it is. So this is FL star. This is the state that we want to talk about. So there's some very extreme strong coupling limit. And this now is getting closer to the truth. So you can see it's a rather almost Rube Goldberg construction. You start with the electron, you fractionalize into holons and spin-ons, and then you take each holon and bind it to some of the spin-ons and put the remaining spin-ons in a spin liquid, which are the orange dimers. And you can say a lot of the words, and you can write down field theories at various stages, but the last stage is where you throw up your hands and you say, well, I don't know how to really describe the binding of the holons and the spin-ons. But that's really what must be happening. And so now I have a state which has all the right properties, at least broadly speaking. It's got density P of electrons, not holons, of spin a half objects. And of course, in the real world, things are not this tightly bound. If they're really this tightly bound, then again, the spin sector of these things would be gapped, and that has various problems with observation. You will get the Fermi arc-like spectra. In fact, we do have a paper with Matthias Punk where we computed the electron spectrum, and it looks very much like the observations in this model. And there's various other approaches by other people. I mentioned the work of Wen and Lee, which philosophically is very similar to this approach. Okay. So I think qualitatively that idea is correct, but implementing it in a way that you can really compute something is very, very hard. And I'll give you our recent ideas on how to do it. Okay. All right. Any questions? I'm talking about things that I've spent many years on, too many, but it's really an interesting problem, I think, and it's relevant to many, many, many experiments. Okay, so.
Question.
Yes, go ahead.
To what extent are all these steps in your construction really distinct? In other
really
words,
what?
when so you had a step, you took one field and you wrote it as a product of others, and then you combine one of these others with something else. To what extent are all these steps distinct? Or is it that there could be just one step that takes you from the starting point to the end?
I think you put your finger on the exact point. So the previous calculations make these steps distinct. You do one thing, and then you have to bind some of the things that you created. And then it becomes very hard. The whole calculation becomes very cumbersome and in fact, almost essentially impossible to carry out. It would be much better if you could do everything in one step. And that's what I'm going to present. Okay, so we'll start with the Hubbard model right here. And now you have to go back and remember way back when, where I wrote this Hubbard model as free electrons coupled to a paramagnon. Okay,
May I ask a question?
Yes, go ahead, Juan.
I would like to understand how do you select the state, for example, the oval shapes, the two kinds, you have select the spin singlet for the spin pairing up, down, minus, down, up, while the other one you select the up and the whole plus.
You meant why the sign plus?
Yeah, so the sign.
That's simply because this sign is minus here. The T, so this binding is due to T, and this binding is due to J, which is the J term, which gives you a minus sign.
So due to energetics?
I mean, yeah, so if you took, if you had a negative, if you had two sides with a negative Heffing matrix element, the ground state is a symmetric state, right? That's the tunneling problem. That's all. So it's just T gate takes you from here to here, and you just get the symmetric state. This comes from the J. Yeah, sorry.
But did you also mention the second one? This the spin and the whole bound state.
Yeah.
Does it need require to be fermionic electrons? Or
so the point is that, so if you remember, the way these things proceeds in actual calculation is you have the electron, which you split into a holons, a boson, a holon. Let me say a holon and a spin-on. Okay. Now, depending on who you are, you would call the holon a boson and the spin-on a fermion, or vice versa. But the point is, no matter what you do, once you form the bound state, which is what the yellow object is, it's always a fermion. It has to be, because you're putting the spin-on and the holon back together. You're putting every holon with a spin-on, but you're leaving some of the spin-ons back. And that's kind of the state you get. Look, this is just to give you a bit of the history. Let me present a much better way to think about it. Okay. So you start with this, and you can rewrite the partition function in terms of some Lagrangian of some paramagnon field and the electrons. Okay. So this you have C dagger d by d tau minus some dispersion of the electrons. And the important term is you get a phi squared with some strange factors that we've worked out way back when, and phi is coupled to C dagger sigma C, the spin of the electrons, okay, on each side. Okay, so this is, the canonical Hubbard-Strohanovic trick. For particle physicists, it's sort of like going from the Gross-Nouveau model to the Gross-Nouveau-Yukawa model. You just take some full Fermi interaction and you couple it with the scalar. Okay. So this is what we did earlier. So now what I'm going to do is I imagine that I integrate out the high energy electrons, and I make the bare Lagrangian of phi a bit more complicated. It's not just phi squared. It's, it's something like this. It also requires a kinetic energy from the high energy electron, d phi d tau squared, plus some v of phi. Okay. And this also we did earlier when we did the theory of antiferromagnetism. This is the paramagnon, and this requires some potential. V of phi, as usual, will have some Mexican hat-like shape, but it's 3 dimensions. This is phi here in some direction, and this is V of phi. So the phi will basically fluctuate around here. And this region is a sphere. It's not a circle, it's a sphere, because there's 3 components of phi, and that's important. All right, so now what I want to do is to take this Lagrangian and rewrite it as a Hamiltonian. So what will be the low-lying states of phi if in this action here? Well, it's basically going to be moving around here on the sphere, and it'll have some angular momentum. So all I'm going to assume is that the 2 lowest states of phi there's an L equals 0 state, where it's angular momentum 0 around this, the S state. And then there's an L equals 1 state, which is threefold degenerate. And there's some gap here, delta. There's many other states, I'll forget about that. Okay. So I have 4 states that I want to keep. There's the ground state, which is fully symmetric, because I don't want phi to condense and break any symmetry. It has some gap to the first excited state, which is finite. In fact, it's probably pretty large because all the U's floating around. But I only keep the first 2. All right. So far, everything is completely, completely standard. And this is the starting point of thousands of papers on magnetism and Fermi liquids. You condense phi in different configurations, you get spin density waves, and agrees with many, many experiments. Not on the cuprates, but on other systems. Okay, so what I'm going to imagine is that these 4 states are the eigenstates of 2 spins. So I'm going to fractionalize phi. So I'm going to say there's some Hamiltonian, delta S1, this is some other fictitious spin, S1 dot S2, which are spin and a half spins. And so the spectrum of this is exactly the same. It's a ground state of singlet, a triplet, and splitting is delta. So that's the undergraduate quantum mechanics problem of 2 spin and a halves coupled to each other with a positive coupling delta. So what have I done? I've replaced this phi by 2 spin and a halves. Okay. So now let me just draw all of that in a picture, and then you'll see how it all comes together. So what I have is the following picture of what's going on. And really, this is just a rewriting of the Hubbard model after a bit of RG of eliminating some very high energy states. I'm not really introducing any low energy states. So here's my original, I'm looking at it edge on. This is the square lattice. And these are the original electrons, which now have become nearly free because all the interactions are coupling to the phi. Okay. And each phi has now become 2 spins. So I have a spin here and a spin here. So I have 2 hidden layers of spins. Okay. And they're coupled together with this coupling delta, which I'm now going to call J perp. Okay, and maybe there's some couplings between them too. You can add them just for fun, but this is the basic model. And then you couple this to this. That was the phi C dagger C coupling, and I'm going to call that coupling JK or Kondo, of course. So what I'm doing is rewriting this model as a Kondo lattice model, except I'm not allowed to introduce just 1 layer of spins, but I am allowed to introduce 2 layers of spins, because in many senses, this double layer is a trivial state. It's a state when J perp is very large, then this double layer doesn't do anything. The spins will just form singlets. That's the L equals 0 state of the paramagnon. Now there's a triplet. And what I have argued in the previous slide is is that if you get rid of the triplet here, you effectively introduce an interaction on this layer, which is essentially the Hubbard model. And you can see why, if there's a spin and a half here, then it'll couple to this and lower its energy. If it's doubly occupied or empty, it can't couple to the environment, so its energy won't go down. And that's exactly what the U term does. It reduces the energy of the singly occupied side with respect to the doubly occupied and the empty side. So that's another way I could have just started with this, This is just a rewriting of this model. Okay. So this model has two phases. And this is where the fun part is. So now if I take the phase where J perp is much, much bigger than JK, then I'm back to where I started, and I have a Fermi liquid. Okay. So, you know, as I said, this state, it's completely trivial. It's just a product of local singlets. You know, or if you weaken the interaction, it's just a filled band, and these states are fully connected. There's no Chern number, no anomaly, nothing. It's just a totally trivial state. If I added one layer, you'd be in trouble because you're violating all kinds of theorems, but you can add two layers. And you're not really adding anything, you're rewriting the original problem in a different way. Okay. All right, so I can get the FL, no problem. But now, and also let me write down the density. Here, the density of holes is 1 plus P, because they're the free electrons. Here, the density of electrons or holes, doesn't matter, is 1. And here, the density is 1. Okay. All right, so now let's look at the other limit. Okay. So if JK is much bigger than J perp, then forget about J perp. And what do we have in the first two layers? Well, it's what we spent the last few weeks on. It's the Kondo lattice. Okay. So these two, so the first two layers will form the heavy Fermi liquid state of the Kondo lattice. Okay. What's the density of electrons? What's the size of the Fermi surface? So what we learned previously, the size of the Fermi surface is large. It counts all the electrons. So here I'm not counting these. I'm only counting the first two. So how many electrons do I have? I have one, or holes actually here. 1 plus P plus 1, which is 2 plus P. So the Fermi surface size is 2 plus P. But everything is mod 2, which is P mod 2. So in fact, I've got a small Fermi surface. Yes.
Maybe you addressed this, but why doesn't this JK couple symmetrically to the both layers?
Yes, because phi is not symmetric. Phi is S1 minus S2, not S1 plus S2. L, if you know a little bit of rotors, yeah, it won't connect. It will not connect. So if you look at the matrix elements, the model I wrote down, you will definitely find a different coupling. Yeah. It's like the anti-ferromagnetic order parameter, which is S1 minus S2. Okay, so I've got my small Fermi surface. I've violated Legend's theorem. Now that should ring alarm bells. You can't violate Legend's theorem without having topological order, right? That's what we proved very generally previously. And this is where the second layer rescues it. The third layer, spin liquid with topological order. Could be any spin liquid, you know, depending on all the details. And there it is. So now you have an FL star state. So now you built an FL star state, not by putting together a spin liquid with free electrons. We put together free electrons with a pair of spin liquids. And we were, well, pair of spins. We're allowed to add a pair of spins because that's really a trivial state with a gap. And it's perfectly okay to add that. It doesn't change any previous theorem. But once you added the pair, you broke the pair apart because one of them formed a singlet with this, and the other one formed singlets this way. So this is the FL state. So let me draw a picture of the FL star state. So the FL star state is something like this. Now these spins are forming singlets with themselves, all kinds of singlets here. And these, are mobile electrons. This is just like the Kondo lattice. So we have a Kondo lattice plus a spin liquid, and that has all the right properties. Okay, so this idea, as I should mention, is due to Yahui Zhang, who's going to start who was postdoc at Harvard, is starting in faculty at Johns Hopkins soon, I think, next month, I believe. Anyway, so, and it's, to me, after having struggled with this for so many years, it's amazing how simple it is when you write it down this way. It's just a little bit of an extension of everything we learned and have known for a while about the Kondo lattice. You don't have to do all of that complicated constructions of breaking the electron and then putting it back together. This all does it in a very neat way. And also, which the other methods couldn't do for you, it gives you a route to a transition. To describing the transition between these two phases, we can also describe that. Well, it gives some very strongly coupled gauge theory with SU2 cross U1 gauge fields, but you'll have to read our papers on that. And we can't solve those theories very well, but at least in principle, there is some theory for the transition. And so now I think the proof of this, is this a valid way to think about it? In the end, can you compute something useful? Can you fit to the experiments? And we're working hard on that, and it all looks quite encouraging. All right. Okay, so that's going to be the end of my discussion of the pseudogap. Okay, and then we'll start talking about the strange metal. So any questions? I'm sure there are, but I'll probably just refer you to our papers. But no, please go ahead.
Subir?
Yes.
Is there an actual substance where you see this transition directly between the pseudogap and the Fermi liquid? Because the cuprates don't have that, right?
Oh, no, you do. I mean, okay, so what you have to do then is put a magnetic field or a high magnetic field if you want to see it in the normal state. And then there are rapid changes in the Hall effect. I mean, it's a bit of a controversial subject. There's also very careful measurements of photo emission at finite temperature, where you see how the spectral function evolves from the left to the right by ZX10 in particular. And they see a very sharp place where it goes from one side to the other, almost saving first order in their observations, not really a quantum critical point. But there are also measurements in the superconducting phase. You can look at various velocities of the quasi-particles as a function of doping, and you see a dramatic change in how the velocities evolve, again, right at a very special critical doping. So there are a lot of indications of something going on at some critical doping. But it is, I should admit, quite, not understood in any unified way, and also, yeah. I mean, I think now that I'm feeling confident that that we're pretty close to a theory of the pseudogap anyway. There's also comparisons of such theories with various numerical studies, and yeah. So the next step really would be to talk about the critical point, and that's what I'm going to talk about. Just give you some rough ideas, but that's a still a much more work in progress.
One naive question.
Yes.
When you integrated out the high energy electrons,
yes.
And then we went to the real space picture, what does it say about the localization of the electronic wave functions? Can they still be thought of as localized at unique sites, or they are spread over?
Well, I mean, in the end, the electron, these are figments of our imagination. There is no delocalizing electron in this direction, it's only in this direction. This is a convenient way to talk about the low energy Hilbert space.
No, I was thinking of the delocalization of electrons in the horizontal direction only, because you have integrated out some of the K modes. Is it?
Well, so first of all, in the Fermi liquid phase, no worries, you can just forget about this. And then it's just the usual Fermi liquid theory. Okay, so I don't think there's any worries here. So let's go to the Kondo lattice. So here I would say it's very similar to how you talk about a Kondo lattice problem, where you have the C band and the F band, and there's a Kondo resonance, and which gives you some spectral weight on the F band, and there'll be something similar here. But of course, these are not measurable. In the end, what you're measuring is the Green's function on this side, and that is computed in this Kondo lattice model. But in the end, you're computing the physical electron Green's function. Let me make another remark. I don't know, maybe this is related to your question you're asking. Suppose I took this Hubbard model, and even suppose I have two electrons here, one here and one here, and I take U goes to infinity. Well, then, we are told that when U goes to infinity, it is J S1 dot S2. Okay, so now if I take this model, then there's one electron here and one electron here, and the wave function of this electron is completely on this side, and the wave function of that electron is completely on the other side. But that's not the reality, because it came from the Hubbard model. And in the Hubbard model, this electron is actually slightly delocalized on the other side. So the point is, in going from the Hubbard model to this model, you have to do a canonical transformation. And when you did a canonical transformation, what you called an electron changed. The physical electron is the electron of the Hubbard model. The electron in the TJ model is not the physical electron. It's related to the physical electron by canonical transformation. So if you compute in the TJ model, you have to undo the canonical transformation to compare with experiments. Similarly, over here, the electron in this model is not the physical model. You had to do canonical transformation to go from the physical model to this model. So even though in this model, the electron appears delocalized, in the original model, it isn't, because the delocalization is entirely a consequence of your canonical transformation.
Oh,
I hope that helps.
Yeah.
Anything else? Okay, great. So, all right. Yeah, okay. So
I have a question. So may I ask a question?
Yeah, please.
So the way you motivated these two extra spins, it looked like there was a symmetry under exchange of the two spins.
There is.
But in the actual Hamiltonian that you're discussing, it does not have the symmetry between these two spins.
Okay, yeah. So this, I think, Subra asked the same question, so let me get into that a bit more. So, okay. So what I had this model where I had some Hamiltonian for some field phi, and phi was coupled to the electron spin density. Okay. Okay. And this phi you can think of as a particle on a sphere. Some particle on a sphere with coordinate phi. It's a rotor. Okay. All right. So this rotor, as moving on the sphere, has 4 states that we're keeping track. L equals 0 and L equals 1. Okay. So now you can ask, and then I'm going to represent this by the spin states. I have 2 spins, and this will be the singlet of the 2 states. And this will be the triplet of the 2 states, and the 3 other ones. Okay. So now the question really is, in terms of these spins, I have two spins here with some coupling S1 dot S2. Okay, so now you can ask, phi is an operator. What does the phi operator do? Phi is like the coordinate of a particle on a sphere, and L is the angular momentum. So the phi operator takes you from the L equals 0 state to the L equals 1 state. So this is, if you go from an S state, you hit the operator R, you get a P state. So that's what phi, this is just phi. Going from, all right. So similarly, you have to ask then, what is the operator here that takes you from the singlet to the triplet? Well, the operator that takes you from the singlet to the triplet is not S1 plus S2, is S1 minus S2. So phi is something like S1 minus S2. So in fact, it doesn't couple symmetry, it couples with opposite signs. Now there can also be another coupling, which is the angular momentum of phi, C dagger sigma C. And this will be the angular momentum of this particle on a sphere would be S1 plus S2. So they have different couplings, depending on the relative coupling here and there. So there'll be some lambda 1 here, lambda 2. So there's no reason for them to be the same. Okay, did I answer that one? It simply has to do with the fact that it's the difference of the spins that take you from the singlet to the triplet, not the sum.
Okay, thank you.
Right. But yeah, there's just, just have to stare at this picture and it's all clear, right? Once you accept this model, it's amazing how simple it is. Okay. Let's see. So now we're going to change gears completely, and we're going to talk about the strange metal. How much? I ended 8, right? Yeah. Okay. Yeah. So we're going to.
Since you're changing the topic, can I ask about something you said earlier?
Sure. Please go ahead.
So about this FL star,
yeah.
You really have two parts of the system. One is the Fermi liquid, and the other is a Z2 gauge theory.
Say, yeah. For example, yes.
For example, I assume that you assume that these two sectors are completely decoupled, or decoupled to very high accuracy. So, which means that they couple only through high energy modes.
Yeah. So I mean,
because otherwise,
yeah.
Because otherwise, there isn't really a meaning to this separation.
You're talking about the 2-band model or the 1-band model?
Either one. In the end of the day, you had some Fermi liquid and a decoupled topological field theory, for example, Z2 gauge theory.
Yeah.
I assume that you have in mind, or you assume that these two sectors completely decouple.
No, I mean, there's a coupling between them, but there's what you have to show is that certain properties are stable under the coupling. So what's stable? One is that there are deconfined excitations in the Z2 spin liquid that carry spin but no charge. And I'm assuming that under the coupling, those excitations still remains deconfined. Okay, they may or may not have a gap, it doesn't matter, but there are deconfined excitations which carry spin no charge. Then in the Z2 spin liquid, there is also a Vizon. The Vizon has a gap. And when you couple it to system to Fermi liquid, the Vizon gap is still present. So I'm also assuming that the Vizon gap is stable under this coupling. For a finite range, you can show that. Of course, eventually it will disappear. So similarly here, in this model, I have the first 2 layers that form a Kondo lattice, and they form give me these pockets of size P. And then last layer can form a spin liquid. It could be a Z2 spin liquid. It could be almost anything. It could even be a chiral spin liquid. And so that has certain topological properties, and those would be stable. So for example, in a Z2 spin liquid, has these 4-fold degenerate states on a torus. So suppose I took the system and I put it on a torus. Now the system as a whole is gapless, but the gapless states from the Fermi surface have spacing 1 over L, whereas the fourfold degenerate states from the torus has spacing e to the minus L. And I'm assuming is that the e to the minus L spacing split states are stable even under the coupling. So yeah, so there's various arguments like that you can make, where you really have to look very carefully at how large the gap is on a finite system size to see that you can easily combine a topological state with a conformal field theory, and the two retain their properties at least. Yeah. Yeah.
So just to continue on that question, is it meaningful to ask how one can tune lambda 1 and lambda 2 in a microscopic setup, and whether L can become a low energy degree of freedom?
Yeah, it's meaningful to ask. If L becomes a low energy degree of freedom, you're probably going to an antiferromagnet. So there's various other instabilities. You can ask various ordered states. And we have various papers on that too. And so you can get very interesting transitions to ordered states also. Some various, you could get, what is the word Senthil had for this? You could get a Landau allowed transition, which is deconfined. For example, you can get some very interesting sorts of critical points. So you could have, you could have a regime where you have a Landau transition and another regime where you have the transition with the same phases, but it's a different universality class. So these are all kinds of things you can build with this, with certain assumptions. Yeah. But if you want to microscopically compute, that's difficult. I mean, at this point, what we are doing is we write down some effective model for the Kondo lattice. We write down some effective model for the spin liquid with a few adjustable parameters. And we work with that to try to fit a lot of data, much more data than their parameters. And it seems to work very easily. That's all I can say at this point. I think we are, to really compute the parameters, you would need to do some very sophisticated numerical calculation. Maybe someday we'll get to that. Okay, great. A lot of good discussion. So now, the strange metal. So I have in mind to talk about 3 or 4 things in the next 4 classes. So one class of things deals with the SYK model and all its properties. It was the original form of it was very much inspired by trying to come up with some model which looked like a strange metal, but with a lot of disorder, because many of the experiments do have disorder anyway. But it's turned out somewhat to benefit that many of these strongly correlated problems benefit from having disorder. They become easier to solve, as you'll see. So that's one of the reasons for looking at the disordered problems, because they give you much control in a regime where you don't have quasi-particles. So so I should say that the general subject we're starting now is states of matter without quasi-particle excitations. Both of these do have quasi-particles. These are the usual quasi-particles. These are the exotic quasi-particles, but they are in the quasi-particle framework. But this is not. Will not have a quasi-particle description. Now, the first model historically, I would say, which was studied, although not in this language, which does not have a quasi-particle description, is the 3D Ising model, interpreted as a quantum model in 2+1 dimensions. So if you take the 2-dimensional quantum Ising model at its critical point, that's a strongly coupled conformal field theory in today's language. It's a very complicated conformal field theory. There's, today you can get very accurate information for some low-lying operators using Bootstrap. But if you wanted to, it's probably got an infinite number of operators. And if you want to know the higher order operators, we don't know very little about it. And so that almost certainly doesn't have a quasi-particle description, but it's very complicated. And also, it's not a metal. It's conformal. It's at a very special, it's an insulator. It's not something you can vary the density. So it doesn't quite fit the bill. What you'd like to have is some model where you can have some control, and also you can vary the density and have some metallic-like character. And to get such a model, you're willing to pay a high price, at least for a while, like introduce a lot of disorder. And that's really the rationale we're looking at the SYK model. And hopefully by the time I get to the end, I'll tell you about some recent work by many people where ideas on from the SYK model are now having an impact on some more realistic model of metals, which have a nice spatial structure. Okay, but let me begin with a very simple model, in fact, a free electron, just to set the stage. And that's just the random matrix model. So random matrices mean different things to different people, but let me tell you what it means in our discussion. So you have a bunch of sites. I goes from 1 through n, and I not equal to j, going from 1 through n, with some Tij, summation, C dagger I, Cj, and some chemical potential. So this Tij is a random matrix, basically. Is a random okay. So what does that mean? Well, each Tij is a random number, independent random number. Beyond that, actually, you don't need anything else. And it's conventional to put a 1 over square root of n here, as you'll see. So we're interested in the limit n goes to infinity of the eigenvectors and eigenvalues of this random matrix. Okay, so that's what's canonically called the random matrix problem. Originally, I guess, appeared in nuclear physics, and a huge amount is known about it. But I'm going to interpret this random matrix problem as a many-body problem. So what I'm going to look at the eigenstates of this Hamiltonian H, not the eigenstates of Tij. So I'm really working in the Fock space of n electrons or some fraction of the electrons. Say this half filled, so I have n over 2 electrons. So I'm looking at the Fock space of n over 2 electrons. So I have n over 2 electrons. The number of states in the grand canonical ensemble is 2 to the n. So no, I should just, I'm in the grand canonical ensemble. Let me not fix the number of electrons. Is 2 to the n, whether the number of states of Tij is n. Okay. But of course, there's a very simple relationship between these many-body states in Fock space with the states here. So if I take a state here with energy E, this is equal to n alpha, sum on alpha equals 1 through n of E alpha, where n alpha is either 0 or 1, and E alpha are the eigenstates of Tij. So you give me a random matrix Tij, I get some E alpha, easy to compute, even for a size 100 by 100 matrix, no problem, I get the 100 eigenvalues. But now I have 2 to the 100, which is a huge number of many-body states. And so you can ask questions about the statistics of E alpha, of which almost everything is known. But you can also ask questions of statistics of E, of which very little is known. Just going from here to here turns out to be a very complicated problem. But many things are known qualitatively. And so let me just, I'm going to kind of review that, what's known. And the reason for doing this, of course, this is
question. So
yes.
Are these the eigenvalues of, are the E's the eigenvalues of T or the eigenvalues of T minus mu?
sorry, this E?
The epsilon, or E. The E on the right-hand side.
The eigenvalues
so
of T.
The eigenvalue.
Yeah, they are the eigenvalues of T.
And what is the role of this?
Well, okay. Yeah, no, I'm just trying to remember what's the best way to put it. Yeah, no, let me say that the eigenvalue is T minus mu. Okay, thank you. Are the eigenvalues, not the eigenstates. The eigen values of Tij minus mu delta ij. Okay, that's just an overall shift. All right. And E is the eigenvalue of H. Okay, this is trivial stuff, but it's important because this can get a bit confusing. All right. And the reason I'm doing this, of course, is once we put in interaction, and especially interaction so strong that there are no quasi-particles, then this description, this decomposition is not possible. The only thing you have available is E, and you have to look at the statistics of E. And that's quite a bit harder to work out once you put in interactions on some of these in this model. Okay, so let me say a few more things.
So you're assuming that the Tij is distributed according to one of the three ensembles?
Let's say the unitary ensemble. Yeah, just make them complex. That's the simplest case. Yeah.
And this is long ranged?
Yeah, it's infinite range.
Infinite
range.
Okay.
Okay, so yeah, on terms of background, I mean, this kind of model has also had a huge impact in condensed matter physics and also various quantum physics problem. It might seem completely artificial, but if there are these experiments where people look at transmission of electrons in quantum dots, and they look at the conductivity and the fluctuation of the conductivity in a quantum dot. So roughly the picture there is the electrons come in on one side of the dot, they bounce off the walls and then eventually leave. And so you need to know the transmission amplitude for the electron through the quantum dot. Now that's a very complicated problem. So that's a problem which classically is chaotic. If you have a billiard, even in a simple billiard, classical motion is chaotic. And so you have to know something about the statistics of the eigenvalues and their spacing to determine the fluctuations of the conductance, say. Now, amazingly, it turns out, you can fit a lot of the data, but just assuming that instead of having a billiards or a quantum dot, you just have a random matrix, and that gets many of the properties correctly. And so there's this deep connection between energy level distribution of Hamiltonians, classically chaotic Hamiltonians, and random matrix theory. And a few things have even been proven that there is this connection, but that's all at the single particle level. Okay, so we are interested in analogs of that kind of connection in the many particle sense. All right, so we'll take Tij mod squared is equal to T squared. And then with the 1 over square root of n, what do the eigenvalues of E alpha look like? So here's the energy E, and I can plot the density of the eigenvalues rho of E alpha. And I'm sorry, I'm going to get all confused with the mu. So for now, let me just remove the mu, then we can put it back in. So what you find that the density of this is this famous semicircular density, and it goes from minus 2t, okay, minus mu, and 2t minus mu, if you put the mu in there. And so what this means is that there's a bunch of levels here. And the average spacing between these levels is basically t over n, so 1 over n. Okay. And the density of these levels is the famous semicircular distribution. So books have been written on the distribution of these spacings and so on. We're not going to be interested in that. What I will show you, well, probably next time, is a simple calculation of the semicircle. That's quite easy to calculate. If you want to do more, well, that's a whole different course on random matrix theory, which fortunately we won't need because the strongly interacting version has a very different physics. All right, so what would happen here? What is the ground state of H? We're interested in, say, the low energy states of H, not of this random matrix. There's also, huge amount of work for what happens at the edge, and all kinds of wonderful connections of what happens at the edge of random matrices and theories of gravity and God knows what else. We're not interested in that at all, at least in this picture, because our edge is somewhere else. If I look at the many-body energy, what is the lowest energy state? Well, the lowest energy state is all the negative. This is 0 here. All these states are filled and those are empty. So this is the lowest energy state. These are filled and that's empty. So I have here, I have my ground state E0, and it's this state. Okay, so now what's the first excited state? Well, the first excited state is what a chemist would call a LUMO or HOMO. You're going to take the lowest unoccupied orbital and add an electron, the highest occupied orbital and remove an electron. So you could add an electron here or remove one over there, and so on. So you'll get a bunch of levels here, which just have to do with things happening here, not happening here, it's just happening here. You add an electron here, you minus, and the spacing here will be 1 over n, because you're adding small particles. So now when we put in weak interactions and you diagonalize this picture basically still works. And what you would call these excitations, these are quasi-particles. You have a quasi-particle excitations that's more complicated with interactions, but what you will still find is that the spacing of the quasi-particle levels is 1 over n. Okay, they're still having, and also this state here is very similar to the next state. You just added or removed a particle. If n was 1,000,000, just added one particle somewhere. These states are very similar, just small changes. You add and remove a quasi-particle, and that gives you this very low energy subspace. Okay. So, however, what happens at higher energies? So first of all, you can ask how large is the bandwidth? So what's the maximum possible energy? Well, the maximum possible energy is the lowest possible state where you occupy these and not occupy those. And the maximum, so roughly the bandwidth here will be with some factor T times n. So the bandwidth is of order Tn. Okay. And in fact, the whole thing is particle symmetric, and up to here also you'll have at very high, some very large spacings of order 1 over n. Okay, so the bandwidth is T to the n. The number of states is 2 to the n. I can't possibly fit so many states with spacing 1 over n. The maximum number of states I can fill here is n squared. Spacing 1 over n, bandwidth n. So n squared state, but I have many, 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 many more. Okay. So what this must mean is that once you get where the energy becomes extensive of order n, then the spacing is much, much closer. And the spacing here is basically e to the minus alpha n. There has to be, otherwise there's not enough space. So how do you get space energy levels that are so close to each other, even in this simple model? Well, you get energy levels so close to each other by having completely different states next to each other. This state could have this level occupied. The next one could have some other states level occupied, completely different, which accidentally happen to be closer. They have to be closer to each other because there's not enough space for them. There's so many of them. So that's kind of what happens once the energy becomes extensive over n, the spacing is e to the minus n. But right at the bottom, it's much larger. And that's an indication. And all of these features hold, even when you add interactions, that this is a system with quasi-particles. Okay. Yeah, I'll just leave it at that. And so here, well, you can also see now this famous energy level repulsion. Doesn't work here. The statistics of these levels, at least for free particles, is very different. Yes.
Can you clarify the sentence you said that these are quasi-particles?
Well, I mean, there are some renormalized excitations with interactions, which you add and remove to the ground state. And the renormalized quasi-particles always have energies that change of order 1 over n, because it's really a one particle excitation with a bit of dressing. And that's really all I meant. So the spacing here is much larger than when the energy becomes extensive. But here the spacing is close for accidental reasons. This is a state with quasi-particles 25, 27, 28 occupied, and the next one is quasi-particle 13, 39, 56 occupied. They're totally different, just accidentally happen to have the energies close to each other. So in fact, these states will not have energy level repulsion. They'll have the distribution of spacing will be quite different than that of a random matrix. So even though these are distributed with a random matrix with energy level repulsion, these may not be.
But
and figuring out the connection is still a kind of a difficult problem. Yeah,
is there an extension we could think of them as particles? About these excitations? So
well, there are these fermions. These are the particles here, the C's. That's the particle. This is the particle here. Renormalize this with some particle hole cloud. Yeah, that's the particle. I mean, some wave function of those particles with some, which are the eigenstates of Tij. They have a very disordered wave function, but it's still a single particle wave function to begin with zero interaction and some renormalization once you put in weak interaction. Yeah. Well, gapless, right? But it's very important to understand how gapless. So n is going to infinity. I'm just studying how various things go to infinity or zero. So this spacing goes to zero much more slowly than spacing of the higher levels. That's all. I mean, these are properties of the thermodynamic limit. Yeah, but yeah, as we'll see, in this particular model, then it becomes, this is why I'm spending so much time on this, it becomes much easier to detect the breakdown of quasi-particles because you just have to look at the energy level spacing, you can see it. Doesn't happen in all the models, but it does happen here. Yeah. Yes. I haven't shown you that, but we'll come to that. That's quite a non-trivial statement, actually. That, yeah, but the next time we'll definitely discuss that. All right, yeah, so, okay, good. I should stop there and get some dinner. Okay. Any other questions before we close?
I have a minor question back on the discussion of the pseudogap phase, just about what the terminology meant. Did the gap was a gap in the Fermi surface, which had holes in it?
Well, so historically, the word pseudogap came about by measurement of the spin susceptibility. So a Fermi liquid has something called a Pauli susceptibility, which is relatively temperature independent. And very early measurements in the 90s, early 90s, I guess, there was indication that the spin susceptibility was going down, much like it would go down for, say, a system that had a gap to spin excitations. And that was the origin of the pseudogap. But I would say, yes, the modern interpretation would be that there is, if you're thinking about the electronic spectrum, then there is a gap at the pi0 point. So where I drew these Fermi arcs, so that I was just drawing, so this is kx and ky. Okay, so I drew these arcs, and then in the Fermi liquid, the zero energy excitation go all the way to the ends. Okay, so this is just the line of the zero energy excitations, but you can now look at the dispersion along this direction. Let's go here. So at pi, go along ky. So you can plot as a function of ky, which is also something you can measure, the energy of the excitation. Now, if you were going along this way, you see these zero energy crossings here in the Fermi liquid. And so you would see in some dispersion like this with a crossing, this is 0. So that's in the Fermi liquid. But if you do those same measurements in the pseudogap phase, you don't see anything here at 0 energy. And if you look at the excitation in this direction, they end up looking something like this. So then there's a gap here, but this is the gap. So on this side, there's no Fermi surface, as would be required by the conventional Luttinger's theorem to have a full Fermi surface. There is no zero energy excitation, and there is a clearly observed gap. Now, presumably this electronic gap is also responsible for the decrease in the spin susceptibility. But yeah, I think most people would agree that's the origin of everything, this gap here.
There's something funny because Luttinger's theorem would require a closed Fermi surface, but it wouldn't necessarily have to reach kx equals pi. You could, for example, have had a circle in the kx ky plane that didn't reach the boundaries of the square.
You mean something like this?
Yes.
Yeah, I mean, those are also seen, but more at higher doping. At lower doping, you don't see anything like this.
Okay.
Yeah.
Okay, thank you.
Sure. I should say also this ancilla model that I presented there. Sorry, we don't use the word ancilla anymore because I learned about its translation in Latin, which you can look up. So yeah, this paramagnon fractionalization model can reproduce this whole dispersion. So this dispersion here basically comes from the dispersion of the Kondo lattice of the first 2 layers. You can get exactly that. Okay. See you on Friday then.
Thank you, Subir.
Thank you. Sure. Great. Have a good day. We have to go have dinner now.